see, am I recording now? And just press enter 7 for number 1. That's not the answer, but just do it, and then I'll see that you did it. Right? Everybody cool with that? Like, check in today by the end of the day. And you'll get full credit for the easiest assignment ever in any part of your education. So I got number 4. Is there anything else we want to talk about with web work? So I think what is the due date on that web work? It's 16? That doesn't seem right since we don't have class on Monday, right? So how about I'll move that to the end of the day on Wednesday. The due date for homework 1 will be moved to Wednesday at the end of the day. And then Wednesday we can talk about any troubles you're still having with that homework. Is this some like legit plan? Cool, awesome. Fantastic. So, number 4 is on the agenda. Like I said, anything else, or just number 4 for today? You've done a bunch of work, Kitra. Is number 4 about, will that help? Just getting that.
Yeah.
Okay, cool. So number 4, at least Kitra's version, was something like this. I think it was just 1 over here, right?
Yeah.
Yeah, is that, okay, cool. And so it asks questions that I certainly didn't prepare you for with just what we talked about on Monday's lecture. So first off, solving this should be pretty straightforward. In fact, they give you some incredible hint, like the initial condition is that y at, like 20 is tangent of 20. It was like a major hint onto what the y of x should be. And you'll know it when you get it. I don't want to take all the joy out, but I will do kind of a slightly modified version of this so that I don't take any joy out of your life, because I don't want to do that. So y prime, I would immediately convert this to dy dx. I would take any derivative, so I would take x dot always and convert that to this, and I would take y dot and convert that to this, because the name of the game, at least on this assignment, is separation, and we want to get that fraction in there to separate. So then we've got dy dx times this cos squared of x, and now I want to make it sine squared of x. So it would be very, very similar. And then that was equal to 1, and so I go to separate, and I would multiply through by the dx, and I would divide by the sine, and then that would get me this, dx over sine, the sine squared I meant. And then I would have to integrate. And so first business is this. And then you look at this, and that can't do it in that form, but what should I do? How should I convert that? All this stuff is like straightforward integrals. What were you gonna say, Chris?
I was just like, I forget what it is, but the 1 over sine squared of x is another trigonomic.
Yeah.
Like, I forget what it is.
Yeah.
It's not secant, I know that much.
It's not, it's the other one, it's cosecant.
Cosecant.
Yeah. So this is actually a cosecant squared here. So hold on, let's just do this. And then this just becomes y, and I'm going to tack the plus c on here. And then this is actually negative cotangent of x plus c. So please do note, I did put a sweet integral table up for you in the content area. There's like the ultimate math table is there right now in content for you. And so you can find all sorts of things like this to do. And then let's say that my initial condition was y at, okay, I'll just use 27 for some reason or another. Y at 27 was negative cotangent of 27. And you should get something for all the work put in, right? And so that would clearly make c equals 0 here. I think that's clear. And I hate, like when mathematicians say that stuff, it's a little grating. And I learned to say it is obvious. obvious that, or it is trivial that, and that's just like an assholey kind of thing to say. Because it depends on who you are, but does everyone see that what this means is that when x is 27, y should equal negative cotangent of 27. That's how to read that. Just to make sure everybody's on the right page with that. So you can see here that when I put in 27 for x, the only way this could be true is if c is 0. And then I get my solution. So this is my solution, my solution that satisfies that initial condition. And then they ask on what interval, and I think this is the trouble spot, right? Yeah, on what interval does this solution exist? Here's the tricky part. So let's go back to the original problem. The original problem, this was all good and well until I did this division. And what's the one thing you can't divide by in math? 0. So I need to make sure that I'm not dividing by 0 anywhere in this problem. And so I need to make sure that sine of x is, I need to figure out where sine of x is 0 near x equals 27 here. So let's actually just take a look at that. In other words, I want cosecant to be defined around my solution, and my solution is at 27. Right, so actually my solution, God, I don't know what cotangent of 27 is. I'm just going to pretend it's this. Could be. Could be. So I need to make sure that cosecant is defined around this thing. Now cosecant is equal to 1 over sine. We knew that. In fact, Chris was coming up with that fact here, that it was something. He knew that 1 over sine was something, and it's this thing here. So I need to make sure that, not make sure, but I need to figure out where is sine of x equal to 0. So where around x equals 27 does sine of x equal 0? So let's look at sine. And you're going to have to look at cosine probably for your problem. So you'll have to do a slightly different analysis, but sine looks like this. Oh boy. Oh boy, that's not good. Sine looks like this. Good Lord. 2 pi, 3 pi, 4 pi, etc. So what I need to do is figure out what 2 multiples of pi does 27 sit between. That's going to be my goal. Because once I divide, so this is sine, right? This is sine of x. Cosecant is the reciprocal of that. So let's think about what it means to take 1 over this graph here. Any place that I have a 0, I'm going to have an asymptote, because this becomes 1 over 0 in all these spots here. So at pi, at 2 pi, at 3 pi, 4 pi, etc. So at every multiple of pi, cosecant of x is going to have an asymptote. And then think about this. The highest point here is 1. Lowest point is minus 1. So when sine is 1, 1 over sine is also 1. When sine is minus 1, 1 over sine is, hope you can see this, getting a little low here. 1 over sine is minus 1. And then you're kind of like moving the points that are here at 0 up to infinity down here. So your cosecant graph looks like this. And then just keeps alternating that way. So that's how I just like hand generate a cosecant graph. It's not like the most precise thing. That's not the best spot, is it? It's kind of rough for some stuff like this. So I need to figure out, so somewhere out here I'm at 27. x is 27, and I just gotta figure out what multiple of pi I'm between. So I might need some calculator friends to help me out. I'm going to divide 27 by pi. If I was doing the original problem, I'd probably divide by pi over 2. What do you get when you do this? 8.5. Cool. What?
8.6.
Yeah, cool, awesome, yeah, definitely. Either, yeah, it's all good. Because all I'm mostly interested in is it takes 8 pi's to get as close to 27 as I need. And then between 8 pi, right, because so what this means is 27 is approximately 8.5 pi. So I'm going to come out here to 8 pi, and then 9 pi's on the other side, and somewhere in betwixt here is 27. And looking at that, it's kind of almost right in the middle, right here. So 27 lives between those two numbers. And so this solution is good as long as x stays between 8 pi and 9 pi. So for the problem, does this make sense? And so the problem that you have, I would divide by pi over 2 and figure out what multiples of pi over 2, say 27, lives between. And that's going to do it for me. Does that make sense? Yeah? Kids, are you sure?
Yes.
And yours are not those, because I checked yours.
Okay.
Yeah. Yours are way too big. The numbers you're entering are way too big. Yeah. Questions on this, friends? Yeah, so the answer for this one is negative 8 pi to, or excuse me, positive 8 pi to 9 pi for my goofy problem that I made up. Sound good? But you'll find out, you'll know if it's good when you try it, right? And then it'll be varying degrees of suffering and joy. Okay. Anything else? We'll talk more on Wednesday. And then if everybody's if people are really suffering on Wednesday, we'll make the due date Thursday or something like that. But so I like to make these due dates as little torches under keisters to just keep you moving forward. One person who's hasn't even been able to come into the class yet, I guess I'm revealing who that will be when she arrives, is almost done with this assignment. But she also had a problem with number 4. There comes half of the incredible number of efforts involved with this. So, I'm talking to the camera person who's watching this, check this out. That's what you need to do. All right. Cool. So there's no other questions. So I would like to make a couple points that lead into today's discussion. I'm going to need, so I asked you to bring your laptops today, right? I hope you got that email. We're definitely going to need those in a few minutes. We're going to do some numerical experiments and some handwritten numerical work, which is kind of fun to do and soothing. But a couple of notes. The first is that, I guess the first is, this is like a meta thing. I put problems in the web work that I want you to ask about. Like that problem. So when you will occasionally be working these assignments and you'll be like, whoa, what is this about? I want you to ask me. I want you to try and I want you to ask me. So that's the meta note. Note 1 is not every ordinary ODE, ordinary diffie-Q, is separable. That's note 1. And next week when we come in on Wednesday, we're going to actually journey into the first class of those, a very common class of those that's not separable. But here's a quick example right off the bat. So e.g., y prime equals x plus y. Really simple, but not separable unless your math is weird. And that weird math would not be correct in this universe. Because when you tried to separate this, there's literally no way to break these two apart in a legitimate way that also like gets everything that's x with dx and everything that's y with dy. So let me just try really quick. I do this. See how the x is now stuck with the dx, which is good, but so is the y. So I can't separate this. This is not separable. This is a very special kind. This is called a linear DE, linear differential equation, but it's not separable. Everything in the web work is separable, so you can't claim not separable as like a legal excuse to not do any of the problems. Those are all separable in homework 1. And then the next comment is that not every separable DE, ODE, can be solved explicitly with integration. Ugh. So here's a quick example. E.g., let's go like really easy here. Y prime equals e to the x squared. So I see this, maybe don't. I just start going through the motions as we do sometimes in math and in life. And then I separate them. Okay. So all legit moves, right? I've literally separated this, done all the good math. That's nothing, this math isn't bad. But when I get to this stage, I'm a bit stuck. We can't do this with any known by hand techniques. The one thing you might try is substitution, right? You might think, okay, that's like, it looks like this. So that would be exciting if it was that, because that's the easiest integral and derivative in the world, right? E is our deep friend in calculus, near and dear to our hearts. So for that to be this, I would have to let u equal x squared, but then du is 2x dx. And no matter how hard I try, I can't get the extra x that I need in there. Do you see how this substitution won't work? And let me just prove it to you if you don't see it. The way I teach integration is I rewrite dx like this in terms of du. And then I come over here and I do the substitution. So this side's going to be cake. That's just y. But this, let's see, so we'd get e to the u, and then dx I'd replace with du over 2x. This x doesn't cancel. The fact that this doesn't cancel tells me that substitution is faulty. Doesn't cancel, so the sub is wrong. And there's really no other sub to do. There's nothing else in there to substitute. You could let u equal e to the x squared, but then du is going to be even worse. So we can't do this one the way we talked about. So how do we take something like this and gain insight? How do I understand this problem? Because, you know, in reality, you're going to encounter all sorts of things that can't be integrated. Or maybe you don't even know how to integrate it, and that's okay. Maybe you're just like, I can't find it at the table. I don't know what I'm going to do. So we fall back on some computers to help us out. Let's talk about how we could solve this stuff with a computer and actually gain insight into the whole thing as a deeper insight into looking at the problems that we see throughout the semester. So first thing I want to talk about is qualitative understanding of a differential equation, as opposed to quantitative. Quantitative is where I got a formula, and I got y equals, and I'm good, and I got numbers, and here's a formula, I'm done. Give me my money, boss. Qualitative understanding of DE means the feel, like a general sense of how does this thing behave. So what we use here are what are called direction fields. and sometimes called slope fields. And they're really cool. And let me do one by hand just to begin with. So let's just take a look at this guy right off the bat. So let's consider this and understand what that is saying. So we're going to view this as information about the slope of the solution relative to points in the plane. So what we can do is think of this as, this is the tangent slope to our solution at point xy in the plane. So I give you a point and I can compute the slope of the solution, and I hinted at this at the very end of the hour and you were probably just like ready to be out of here. But when we had that hyperbola like this, and I think it was x times y or something like that, I said, oh, you know, I could compute the tangent slope here. And what I was getting at is this, a little bit of a lead-in. So what I mean here is more precisely, got x and y, come to the plane, and this is my slope right here. Just think of this, derivatives are slope. So the slope information is really easy to understand. I can come down to the plane, and at the point 0, 0. So at the point 0, 0, I can compute the slope, the tangent slope to my solution. So here, m is just the sum of the x and the y coordinates. Use the formula on the right. So slope is 0 here. And I draw a little horizontal arrow to indicate a 0 slope. That's the tangent slope to the solution. Let's move over a point. At the point, let's get some huge scale here. So this is the point 1. So that's 1, 0. At 1, 0, m is equal to 1 plus 0. So here the slope is 1. So I add a little diagonal line to indicate that the tangent slope there is 1. And I do this at every single point in the plane, or a sum. I do this, you know, at a lattice of points in the plane. What's going to be the slope right here in the middle of those two? Half, yeah, right? Because this is 1/2, 0. So watch how I indicate this with I try like half slope. That's 1, so it's half that slope, so it's a little bit less intense right there. And then up here, let's try to get my units correct and let me not block Olivia's view of the whole thing here. What's the tangent slope here at 0, 1?
Still marginal.
Still, how'd you get that? How'd you come? So are you saying horizontal? Are you saying a slope of 0?
Would it still be?
Well, let's see. What is this coordinate here? So let's talk. Who am I talking to? It's Chris. Hi, Chris. Just like voices coming to me. I'm used to it. But I have to remember it's people talking to me this time. So we got 0, 1. So what's the formula for the slope?
X plus y.
And what's the sum of the x and y coordinates?
1.
So not 0, right? But
Yeah.
rather, yeah, you see what I mean? It's cool. No, it's good. Thank you. I really appreciate that. So m equals 1 at the point 0, 1. Let me stop, because Chris is like going out on a limb, like doing talking for everybody. Does that make sense? All right, cool. Where's the slope 0? So look, here's the slope 0. Where is m equal to 0 in the plane? Here's a more like a totally different kind of more interesting question. What is the collection of points where the slope is 0?
Is it just like the negative diagonal, like the 1 to 1?
Yeah, how'd you get that? Yeah, you're right.
Oh, they just have to cancel each other out. So when x is positive, y has to be negative, and they have to be the same.
Exactly. So check this out. So where's the slope equal to 0? Answer, where dy dx equals 0. I.e., where, now go to my formula, x plus y equals 0, and then let's put that into a form that makes our minds happier, y equals negative x. So all along, and Kitra was doing like hacking her way through this, like a math ninja, coming down. So all along this line, anytime the solution crosses this line, and I put those arrows to the right because we generally think of flows to the right, all along there, I've got a horizontal slope. Where's the slope equal to 1? Somebody else tell me. So everybody, take a moment. At what points in the plane is the slope of the tangent to a solution equal to 1? So everybody finds out, maybe plot it out, and then maybe if you're already answering that question, do negative 1. So we're going to do some of this by hand before we have their robot friends do all the work. I'm going to wake up the robot. Arise. Gosh, okay, well that sucks. All right. Yeah, and then after you do that, where is the negative 1? And answer that question as well. So it just like won't let me log in. I don't remember. I have like this other password. It's maybe okay. Maybe I know what it is. Does anybody have World Class open? Oh, cool. So in the content area, there's like a slope. There's tools, and then there's like a second one where I'm like, here's a better one because I found one, and then I was like, here's a better one. Can I just see what the address is for that one? Thank you. Bluffton. Okay, awesome. Thank you. I just need that for the search term, and that'll get me there. Thank you. Boom. Beautiful. Perfect. Thank you, Chris. Okay, so slope is going to equal 1 when x plus y equals 1. And that means y is equal to 1 minus x, and that is a slope of a line of slope -1. So parallel to this line, y-intercept of 1, right? Because if I write it like this, maybe that'll help. mx plus b form. So it goes through 1. So right here, where the slope was 1, and the slope was 1 down here, and that's clearly not going to be parallel. So let's see here. Like that. So that's got to be 1. All along here, the slope is -1, which is literally perpendicular to that line I just drew. We're just going to do this once today. It's a little painful and then messy there. And then the slope is going to equal -1. m equals -1, where x plus y is -1. I just replace the slope, the dy dx with -1, so y equals -x minus 1. That's the line that goes through y-intercept -1 of slope -1. So I come down here, and it's lovely symmetric. Here's the erasers in this place. Fresh. Huzzah. Okay, there we go. So slope of -1 on this line. Now, there's something really interesting happening on this one, which is why I asked about it. All along this line, so here m equals 0, here m equals 1, but here m equals -1. And I can't see the arrows because they're actually on the line, because the line already has slope -1. All right, so let's stop for a second. Does that make sense? Let me know. Does anybody have like questions about this? Something unclear? So I'll give away the next one. Notice that the slope of the line is actually equal to the y-intercept. The slope of the things on the line is equal to the y-intercept. Here the y-intercept was 0, slope is 0, 1, 1, -1, -1. So down at -2, the line that intersects at -2, which is like, you know, here on the wall. Just we know. Here the slope is -2, so it's actually a little steeper than this line. Like so. All right, now we got enough to figure this stuff out. Now we can start this is like a current. Imagine this as like air hockey. Do people play air hockey still? Yeah. So like an air hockey table that's really kind of messed up because it's got a bias to it, right? It's got little jets of air shooting in all sorts of ways. Or like think of it as like a lake, surface of a lake plastered up here on the wall. And if I put a leaf on here, if I put a leaf down right here, so here's a little leaf, I set it down there and I'm being very meditative, and I'm like, where will the leaf go? Let the current take it. Well, let's see, what would my y-intercept be about right here? That looks like about -3/4. So it kind of heads off, not this steep, somewhere between these two, so it heads this way. But by the time it moves just a little, it's actually in a new current, right? I've moved just a little, so what I see is that every time I move to the right a little bit, I'm in a different current line. And eventually what's gonna happen is, ooh, it's probably a little steeper than that. Damn you, where's that eraser? There it is. It goes something like this. And then when it crosses this line, it's perfectly horizontal. And that's not perfectly horizontal, but then we come up. And you're just following the next arrow in the line. So like when I move here just a little bit, I pick up the next tangent arrow and it's like this. Then the next tangent arrow is like this, like this, like this, like this. And then eventually horizontal, and then they start picking up positive direction, and then finally it's like that. And then the next one, when the slope is 2, I'm up here and I'm going steeper and steeper and steeper like this. What happens if I put the leaf here? Just straight down. So it's kind of like if you're a scientist, or you've had some physics and you know this term equilibrium. It's not really equilibrium, but it doesn't really curve. It's certainly a straight route. So I put that leaf on there and it just kind of cruises down that way. What happens if the leaf is a little bit to the left of this? I'm trying to do this for you, Olivia. Is it okay?
Yeah, I can see.
Okay, cool. And I put the leaf here, and then the slopes are negative, so I start seeing this kind of motion. And then, like right when I cross that one, the slope is the perfect whatever there. And if I just did this all over the plane, what I'd see is all the possible solutions that are consistent with all these curves And all they have to do is have a consistent, that's fun. This is really pretty fun to do, actually. So we get a sense of all the possible behaviors in the plane. That's a qualitative understanding of the problem. Because now I see that sometimes, depending on the initial condition, I will head off to positive infinity. But sometimes, depending on the initial condition, I'll head down to negative infinity. And it's a really fine line here, right? Like this is a very delicate line right here. If you're on this line and I just blow from this side, you'll end up shooting up to positive infinity. If I blow from the other side, you're falling down this way. So this is how we get a sense. Now, you're going to have a computer do this for you. Because this is what computers are made to do, repetitive, simple things over and over again very quickly. So, friends, let's take a look at, open up your laptops, please, and go to World Class, hopefully with better success than I had. And in the content area, go to the second app, and let me get that going here for me. Let's see some mood lighting. Nathan, sir, would you like that? Lovely, yeah. Good. Okay, so let's first see this little button here that I'm highlighting. It says RK4 H equals 0.1. Just click on that and go over and select Euler. Because that's actually the first method we're going to talk about today. That RK4 is much more sophisticated than we'll talk about what it is, but we're not going to do it. So yeah, go to Euler and then H equals 0.1. So check out the problem. The ODE is exactly the problem we have here. dy dx equals x plus y. Look at the flow. Did I lie? No, I did not. That is the freaking flow. Generated by the greatest computer. Well, probably not for long. Probably not anymore in any way. But depends on what we're talking about. But here the computer's done exactly what I was talking about. And if you click on here, you will get trajectories. So you can just click on the plane anywhere, and it actually runs forward and backward in time, and we can fill the plane with a complete understanding of what every possible solution to this differential equation is. And that's really beautiful. It's fun and beautiful. And we could do this one too. But let's not yet. Let's do something a little simpler. Let's start off with a pretty chill differential equation. So let's change, so click on the actual equation itself. And inside the x plus y, just replace that with y. And see, notice how you can change it to different variables. You can have dy dt, dx dt, we want dy dx. And it instantly repopulates everything with that new differential equation. So it alters all the trajectories that we had to match this new one. Let's do one other thing here. Let's go up to initial points and click clear all curves. I found that button, that box that's clicked, didn't seem to work. It honestly took me a long time to figure out how to clear all the curves. So I was pretty proud of that. So let's look at an initial value problem. That's a very simple one. And I'm going to actually ask you to take a moment before we head into this foray to solve this by hand. Could you please, dear friends, solve dy dx equals y with this initial condition, y at 0 equals 1. This is a fundamental equation. Really important. So we can all see that, okay. And Tom, do you prefer Thomas or Tommy?
Or Thomas.
Thomas,
I got,
okay,
like,
Tom.
changed in my email when I declared my major for some reason.
Got it, okay. But you prefer Thomas.
Yeah.
You've got it, my friend.
Yeah.
You can see this okay from over
Yeah.
there? Okay, great.
Yeah, thank you.
I'm kind of writing out my whole narrative here of, I think something I actually already did on Monday, but it's worth seeing many times. Step one is to get that general solution. Any of these along the way are cool. Like if you got to here, good work, you solved it. But I would like you to get what are called explicit solutions. So explicit means it's y equals f of x. This is implicit. Totally cool. Not as useful. This is much more useful. So this is the explicit. And the general solution is the thing where you have the c. That's before we've used the initial condition. When I go for the initial condition, I'm going to let x equal 0 and y equal 1 and figure out what c has to be for that. You will find out c has to be 1. So y equals e to the x. And let me know. So let me stop. I'm going fast. I want everybody to come along for the ride. It's like your class actually. It was right there. Just thinking of my lessons. Yeah, I think that's going to be rough just because the way this class is laid out. This is way too far. So. Any questions on getting y equals e to the x? Yay! Outstanding. So, what if I gave you this problem and then I said, find y at 1? Well, you would go through all of this. You would get this solution, you would plug in 1, and we would just get y equals e to the first. In other words, y equals e. So e, just beautiful old e, right? Who knows e to some places? Okay, cool, 2.7. That's good. If you know that, that's golden. 1, 3. Close, it looks like a 3. 8. 1828. So look, 1828, 1828. Most famous day in history that I have no idea what it means. It's in E. It always just looks like some shit happened on that day, right? That's the day E was made. I'm just making that all up. But this is real. 2.7, if you can get that, you know more than like, 99.9% of humanity. And then if you got this, and into the upper echelons. So anyway, so y is approximately that at 1. So that means, now let's come back to this app. And so go back to initial points. So click on the window that says initial points and clear curves if you put any on there already. what we're gonna do is hit submit. So after you enter, make sure you put 0, 1, because that's the initial condition for this problem. X is 0, Y is 1, then click submit. And what it's gonna show you is the solution moving forward in time and backward in time. So in other words, what it's showing us is not just positive X, it's showing us the whole thing. Ooh, oh my God. So that's 1 right there. So that's just e to the x, that's y, that's x. We are at, what we want is the value at 1. So we want that point, which should be this number right here. Is that what we got? Well, the way to find out, they don't have any units on this graph, so click on table at the top. And what you'll see is this little table pop up, and this is doing approximation. So notice up here it says h equals 0.1 and Euler. And I'm going to explain what that means. But they're using a numeric method to approximate the solution. And here's what we came up with. Here's the approximate solution, 2.59374. Pretty far off. Pretty bad, because we know the actual solution is 2.71828. So that's off by a significant amount that we could figure out. So let's try something else now. Let's go up to where it says Euler. And click on over to where it says Euler and drop that menu down. And go to where it says improved Euler, and then in parentheses it says Hahn. Did things get better? It's actually accurate up to like 2 decimal places now, right? Can you see that? At 1, now we've got 2.71. Little bit better, for sure. Not perfect, because we also know that it's 1, 8, 2, 8 for these next decimals. But we're better. We've actually improved things, and I would hope it would improve it. Now let's do one more. Notice how there's a whole selection of methods here. Click down on what it says Runge Kutta RK4. And how did we? This is what we like do brain surgery with, right? Like this is what you're using for my brain, please. Runge Kutta. Because now there's a bunch of decimals and accuracy missing here, and so it's probably not perfect at all, but looks damn good. 5, what have we got? 6 decimal places there. 5 looks real good. So I want to talk about what just happened and how that all came about, and that's going to take us to the end of our time here today. So I'm going to shut this down for a second. But now you know how to operate this thing. So keep yours up, though. Just keep yours up. But I need this board space. And Nathan, sir, please illuminate the board. Thank you. Many thanks. Cool. So let's talk about what all that meant. So first off, here's a nice space right here, okay? Yeah, so numerical solutions. So first off, let's talk about what Euler's method is. It's really intuitive, and everything I've said hopefully gets us set up for it. You might have even seen this in Calc. I think in Calc 1 we do this maybe here. I remember kind of doing it for sure, but we don't do the subsequent ones. So first off, in Euler's method, we want to solve this initial value problem. Y prime equals f of xy, or x dot equals f of tx, doesn't matter. And then we've got an initial condition, which means that when x is x naught, y is y naught, and we have this initial point in the plane. So, Euler's method is really really intuitive. Euler was just otherworldly in his understanding of this stuff. I mean, he got a number, right? You don't get a number from, you know, I don't know what, anything other than what Euler did. I could think of lots of things, and so can you, because that's probably the stuff we're doing, because we're not Eulering out. Not that you couldn't be Euler, but I'm not Euler. I can guarantee that. So, how does this work? Well, we come here, and it's a really simple idea. First off, we set a step size, and that's what that h was. So set h equals step size h. And in the example that we looked at, it was 0.1. I'm not going to use that number. I want to use the generic, the open, just the variable form of it. The finer this is, the better the approximation, just like everything calculus oriented. The closer things are together, the better they are. The more of things that happen, the better the thing that comes out in the end. So what we do is step one, let's just kind of initialize this thing here. We're going to get the slope at the initial condition. And that's our formula for the slope up there. So m is equal to f at our current point. That function on the right, that gives us the slope right here. Step two. Follow that slope, follow in that direction for this long. So step two, whoa, I don't need to write that, I'm just saying it right here. So step two is find the change in y using this slope, using m and step size h. So let's think about how this would work right here. So here I've got this thing of slope m. So this line right here has slope m, and I'm moving over h units. So the step size h is how much x is going to change by. So this is going to be x naught plus h. That's going to be the next point that we plot. And we're going to use this slope for the whole thing. So we're going to head across and travel h units across. How high up do I go? Well, I go up the slope times h. Notice that if I take this number and divide it by this number, I get the slope m. So that's got to be how high up I go. Does that make sense? Yeah? The delta y, so delta y, the change in y is just going to be the current slope mh, which is actually f at x naught y naught times the step size. So we get this new point. Step three is find the new point, new y coordinate. And the new y coordinate, y new, equals y old plus delta y. That could, if it's negative, we go down. If it's positive, we go up. The way I drew the picture, it looks like we're going up. So in this case, it's just going to equal y sub 0, and we're going to call this y1, the next y, equals y naught plus m times h. Oh, sorry, I already got the formula out here. F at x naught y naught times h. Update x. So x1 is just the old x plus h as well. Move over h units, go up this much, plot the point. Plot point or connect, which the program was doing, it drew a line segment between those two. Let me stop, does that make sense? Any confusions? Okay, cool. Repeat. So now this is our new point right here. So this is x1, and then this is y1. Grab the slope data here and repeat. So let's put that here and let's just write the algorithm out. Repeat. The algorithm is this. the next x, x sub n plus 1 equals the old x plus the step size. The next y equals the old y plus, we'll put the h out in front, sure, why not, doesn't matter, you can put it back. F of x sub n, y sub n. So this is your current slope, this is your current y coordinate, and then we just update like this. And repeat this until you get as much of a solution as you want. So what you're going to get is a collection of line segments. The x is always going to step by a regular amount, so this is going to be x naught plus 2h. That's x2. And then maybe it turns down, and then maybe it goes up, we don't know. Draw that picture. The finer h's, the smaller h's, the better that picture's going to look. So we saw how well that worked. I don't even remember what it gave us. It wasn't good though, right? Like we wanted 2.7, 1828, and we got 2.4. Was that like something like that? Yeah, so this method is really prone to error if the step size is not, micro-sized. And even then, it's still going to propagate error wildly. So this method, that's the problem with Euler's method. It really spreads the error. So then Euler's method was improved. And it was also simultaneously improved by a mathematician named Hahn. And a lot of times this stuff happens, all over the place. And then somebody, whoever publishes it first or whatever, gets their name known for it. Like Euler, didn't he have enough? So we'll just call this Hahn's method from the rest. Yeah, Euler we're done with him for today. So Hahn's gonna get, and I'll just put improved Euler. Because this is cool. This is a really cool idea. And maybe it was Hahn who did it. I don't know. I honestly don't know the history. So the idea is this. We're kind of going to do Euler's method. So let's say we're right here at x sub n and y sub n. So we're at this nth stage. So we're at the nth stage of this process. What we're going to do is do an Euler's method, and we're going to project out and grab this next point. And then we're going to grab the slope here and average it with the slope here. So Hahn's method reaches out into the future using Euler's method, grabs that slope data, brings it back, and averages it with the current slope data. And so you get more information for sure, right? You've got twice as much information. You know that if things are going to get really steep up here, you incorporate that into this current one. So the idea is to reach one step into the future via Euler's. Grab the slope data from that predicted point. That's not an actual point, that's a prediction. But that slope data is probably closer to the truth, or at least it's more information than you had about the future when you were just using one point. Grab the slope data there and average with the current slope data. So let's see what that would look like. Our iterative scheme is going to be like this. X sub n plus 1 is going to equal x sub n plus h. That's my n. It looks a lot like my h. The x just keeps ticking along. This is always going to be step size h. That's one of the easy parts and also one of the downfalls of all these methods, except for the one that's one of those methods listed on that list. But x just keeps ticking. This doesn't change. Keeps ticking regularly. What is going to change is our y. So y sub n plus 1 is going to equal our current y, so we're still gonna adjust our current equation, but we're gonna take 1/2 of the current slope data. So remember, here's our equation. Let me put this back up again. We're gonna take 1/2 of the current slope data. So this is current slope. Plus the slope at x sub n plus 1, and which is easy to find, right? We can just add h to it, comma, y sub n. So now it's gonna look like this. I'm gonna put this in as my y coordinate here, because I'm grabbing from that y coordinate. So y sub n plus h f of x sub n, y sub n, and then that's the function within a function. And we still have to multiply that by step size h, and just travel just the right amount. So that's improved Euler. Now, on that list, that last one we did that kicked ass so efficiently, that's a Runge-Kutta method. And you got the basic idea here. So let me stop before I even go there. Any questions on that? Yes, yes.
Just in this last part with the y equation where it's f of x n plus 1, like halfway through, why is it not y n plus 1? Like, why is it just y of n right after that?
Because, so this is actually, so this would be yn plus 1 via Euler's. So imagine just doing Euler's once. And then we get this point here. So this is x of n plus 1, y of n plus 1. We grab the slope here. So that's what you're seeing here. This is actually the Euler's for y of n plus 1. And I think you're thinking right. But I'm just putting the formula in for it. So we first predict y of n plus 1 using Euler's, and then we grab that slope data there. So this is slope at the point, maybe this will make it clear, at the point predicted by Euler's. Does that help?
It makes sense that like this, the whole piece is y of n plus 1.
Exactly, yeah, it's very complicated looking, but yeah. Good question. Any other questions? All right, so that last method, the Runge-Kutta. Runge-Kutta is a whole class of methods, and if you were doing science, this is what you would use. You would use a Runge-Kutta method if you were doing some real simulation, if you were predicting some sort of something important that mattered. You saw how good it was. So the Runge-Kutta method is something like this. So Runge-Kutta, it was two people who came up with this idea. Involved doing multiple predictions and averaging them together with a weighted average. So Runge-Kutta, and I'm not going to write out the whole thing here because it's actually really complicated, but let me just show you what the idea is. We do like an Euler's prediction out just a little ways. And then we grab that, and then we do an Euler's prediction from that point out to here. And then we do an Euler's prediction out from there, and we grab this point, and we take all these slopes. So let me write this out. So you make multiple Euler-esque predictions into the future. That word is future. I can't, it's too late. Too late in the week. It's too far from it. I could have fixed it by now. So make multiple Euler-esque predictions in the future. And so they're kind of this recursive thing. You use Euler's to go here and then pretend that's your point, make a prediction from there, pretend that's your new point, make it from there. Grab all those slopes, grab the slopes at each predicted point. And then and then do a weighted average of those predicted slopes, of the predicted slopes at those points. For years. To get the slope you'll use. So with this RK4 that we saw there, uses 4 averages, or uses 4 samples, sample points into the future. And it weights them like this. Weights, so the first one gets a weight of 1, and then the middle 2 get a weight twice the first one and the last one. Kind of with the idea that this middle data weighs more than the previous one. So we weigh the center 2 predictions more. Than the first and last. That's a Runge-Kutta 4. Whatever this number is here for the Runge-Kutta method, that's how many places out you're grabbing. So like RK8 or something like that. There's one method on there. I don't have it up anymore, but you have it. And, oh, I do have, okay, I have it here. So I just want to show you one more method. And I wish this thing had more precision. But if you click down that Runge-Kutta-Thelberg, RK45, that sounds insane. I just click on that really quick. And no, that's not it. I thought that one had a variable step size. No, that wasn't quite what it, oh. Is this not working? Oh, you have to click back on the graph. That's it. So if you click RK Thelberg and then go back to the graph and click on the graph and then go to table, you'll see that the step size varies, I think. Is that correct? So try that. Go to RKF, come back to the, click on the graph, and then look at the table data, and you'll see that the step sizes are crazy. Is that true or false? Let's see. Oh, it's like one.
I'm just not sure which one of these is supposed to represent the step sizes.
Oh, here. So look at the difference between. So the x. So look at the x and the difference between subsequent. No, I guess it's not. No, maybe not. Never mind. Ignore that. What an anticlimactic end to everything. Completely wrong. But the best methods actually adapt their step size depending on the slope so that things don't get too crazy. If the slope starts getting too steep, they shrink the step size so that accuracy is maintained. We won't be doing that. So I think one time I'm probably going to ask you to do an Euler method by hand and then like one step of an improved Euler. But that won't be until we come back. It's good to do it by hand. Just once. Just alrighty, friends. That's it. We don't meet on Monday. Weird. So weird. Already. We don't meet. But we will be back on Wednesday. If you have any problems, I'll be around in my office on Friday if you want to cruise by. I'll be there like 12 to 1. Like that, cruise on by. If you have any problems, email me if you have problems. And please do significant work on the homework by Wednesday. Oh, please. Downstairs. Okay,
Container within a container, think about it.
good.
Hey, it's
You hate it? You know, my friend who's a teacher.
Oh, yeah, you had it like that.
Oh,
Sorry, thank you.
okay.
It'd be pretty funny
If you're not live, we're gonna
you back.